Greetings, welcome again to this course on CFD. Today is the last class for this week. Last class we had seen details about interpolation, different types of interpolation, particularly central difference type of approximation, pure upwinding, power law scheme, hybrid scheme, and so on. In today's class, we will focus mainly on a scheme called quick, and we will see the merits and demerits of this particular quick scheme. Quick, otherwise called quadratic upwind interpolation scheme, it uses 3-point upstream weighted interpolation. A quadratic fit is made through 3 nodes, and what are those 3 nodes? One node on each side for a particular phase and one extra node in the direction of the flow. Because one node extra is taken in the direction of the flow, this also can be classified under the category what is known as a upwind biased scheme. Let us take this illustration. In this illustration, P is a node of interest and you construct a control volume around that node, and respective node on the right side and left side are also marked. So, in this case capital letter E and capital letter W. Then one more node is also marked, which is west of west, that is shown here WW. And for this illustration, the flow is considered from left to right as shown here, and you are interested to find out value of the variable on this phase, west phase, which is marked here as UW. And you decide to have a coordinate definition as shown here, x and y. So, with respect to the coordinate definition, the flow is from left to right and it is positive. Then phi variable value at that phase is related to alpha 1 phi at W, then alpha 2 phi at B, one more node in the direction of the flow, that is WW, which is given here as alpha 3 phi WW. So, you can observe this is the phase you are interested to find out. You have one node on either side and one extra node in the direction of the flow. Now, let us take the next case when the flow is from right to left as shown here. With respect to the coordinate definition that you are using, the flow direction is negative. Now, we want to find out for this case variable on the phase E. Such case the expression is as shown here, phi at E, that is on this phase you have 2 neighboring nodes, one at E, another one at P, one more node upstream in the direction of the flow, that is EE. So, using these 3 nodal information, you can evaluate variable value on this phase UE. The corresponding expression is shown here, phi at E equal to alpha 4 phi at P plus alpha phi at E plus alpha 6 phi at EE. Coefficients alpha 1 to alpha 6 are to be evaluated. Let us also have another description. So, here is an example. So, in this figure again P is node of interest, control volume is constructed around the node of interest, and the coordinate definition is also given as x y as shown here. If you are interested to find out u on this phase, that is west phase, which is shown here in red color, then it is evaluated based on phi at W, in other words U at capital letter W, that is a node, then another node here, which these two nodes are nodes on either side, then one more extra node in the direction of the flow, which happens to be in this case node at E. So, we have to consider U value at E node, U value at P node and U value at W node, then you construct a quadratic fit, then you evaluate coefficients, based on that you will get variable value on this phase. Similarly, another situation for value on this phase, that is E, you have node E, capital letter E, that is on the right side of the phase, and node P, which is on the left side of the phase. So, these are nodes available on either side for this phase E, and one more extra node which is in the direction of the flow, that is EE, marked, that is node marked by letter EE. So, if you look at the quadratic fit, that is marked in this color, which is running through these three nodes, phi at EE, phi at E and phi at P. Now, let us look at these details with some more information. So, we have to know how to do in the case of near boundary. Near boundary, you have a node which is marked here as a P, then this example right side, right boundary, there is a value given by the boundary condition, that is marked here as phi at RB, phi at B. So, beyond this you construct another node which is known as a mirror node, and that mirror node, for convenience sake, it is taken at the same distance as the distance between P node and the boundary. So, this node, that is a mirror node, which is kept at a distance, same distance as distance between node P and right boundary. Now, we need to evaluate or get an idea of value of the variable at this mirror node, because we have considered the distance same as between P node and right boundary. We use linear approximation, hence it is written here phi at E mirror equal to 2 times phi at RB minus phi P. So, to evaluate the value of phi at CV phases, we employ quick scheme, and for the nodes I minus 1 and I minus 2, where I is in the direction of the flow and it is an immediate downstream node with respect to the phase. So, this particular formula is a generalized formula, whether the flow is from left to right or right to left or wherever you want to find. So, that is what is given here, phi at any phase, and for uniform spacing and in one dimensional, the formula is already evaluated and it is shown here as 6 by 8 phi times I minus 1 plus 3 by 8 phi I minus 1 by 8 phi I minus 2. So, in this, what is I? I is the direction of the flow and it is immediate downstream node with respect to the phase you are interested. Then you have I minus 1 and I minus 2. Let us see how to actually get idea of this by taking example. So, if UW, that is your interest variable value on the west phase, if it happens to be greater than 0, that means it is positive, then phi at W, that is of interest 6 by 8, and I is given here as a node in the direction of the flow immediate downstream. So, for the west phase, immediate downstream is a node of interest, that is phi at B, I minus 1 is on the left side and I minus 2 is to left of W node, which is phi at WW. So, this formula, which is derived for uniform equal spacing, is a generalized formula and you can apply this for any side for any direction. If UE is greater than 0, this is another example, then you can understand how to use. Again for UE greater than 0, which is flow again from left to right case, I is immediate downstream node is phi at E, then I minus 1 is on the left, which is phi at B, and I minus 2 which is left of P node, that is phi at W. So, we already learned from diffusion equation, we apply central type of differencing to evaluate derivative on the phases, and for simplicity sake we assume it is one dimensional with the equal area. So, AE equal to AW and A. So, if you put convection term also, then we get final discretized form as shown here. So, this F is a flux and subscript C stands for convection and E stands for at the phase E. So, FCE at phi E minus FCW phi at W phase equal to FDE multiplied by phi E minus phi P minus FDW multiplying it by phi P minus phi W. In this right side term is actually diffusion term, and we learned this before. The new is only convection term. We have learned that also how to evaluate variable value on each phase. So, if you apply now quick type of approximation to get this variable value on phases, you get this substituted, we have just now seen. So, we can substitute for phi at E and phi at W by quick approximation. So, you get this expression. Once again, in this expression if you look at phi P is the node of interest, and that term appears in all the terms here. As we did before, we collect all these coefficients multiplying phi P, and that is the node of interest or unknown, and put them on the left side. All other quantities are supposed to be known and take them to the right side. So, once you do that kind of rearrangement, you get final equation as shown here. So, you can actually verify whether they are done correctly. So, this term on the left side is a coefficient term for node of interest, and on the right side they are all supposed to be known either from previous iteration or as part of the current solution. So, this node of interest P, it runs for this case of 1D from left to right. Now, when you do that, you get system of linear equation, then you set up a matrix and invert, you get solution. So, as we did in the case of diffusion equation, this equation is also now written in the standard form as shown here. AP phi P equal to AW phi W plus AE phi E plus AWW phi WW. So, if you are able to recall, compare this expression with the expression that we obtained for central differential scheme or pure upwinding, and we can tabulate as we did in the case of diffusion equation. So, AW, AE, AWW and AP, these are terms in this equation, and write corresponding coefficients, and we can again observe that coefficients for AW, coefficients for AE, they appear as term in coefficients for AP. Hence, we replace them with the corresponding coefficient, that is A at W and A at E. In addition, for this quick formulation we get a similar expression, so that is A at WW, and these are additional terms. So, it is necessary only to calculate coefficients AW, AE and AWW, and they go into the expression of AP also. Hence, the only new term that we have to calculate is FCE and FCW to get coefficient value for AP. Now, all that we have done is for one side, we will try to extend it for other side. The generic expression for quadratic fit is shown. Now, UW is less than 0. In the previous case, UW was greater than 0, UE was greater than 0. So, we follow now for UW less than 0 and UE less than 0, that means the flow is from right to left, negative. Right. So, again try to identify for any particular phase of interest, I is in the direction of the flow. So, in this case it is from right to left, and you are trying to find out for west phase in the direction of the flow, west phase immediate downstream node is actually W node, that is what is shown here. Then I minus 1, that is to the right of W node is P, and I minus 2, that is to the right of P is E node. So, corresponding coefficient values are used. So, all that you have to do is identifying what is I for any particular phase and for the corresponding velocity condition. The second case, UE less than 0, again the flow is from right to left, negative velocity. For the phase E, I node, which is immediate downstream node in the direction of the flow, is P node, and I minus 1 is a E node, and I minus 2 is EE node. So, we have to remember always the one dimensional terminology, then you can immediately identify what is I minus 1 and I minus 2. So, we follow the same sequence employing central differencing type of approximation for a derivative which is used in the diffusive term, and employing quick type of approximation for the evaluation of the variable at the phase, then we get discretized form of the equation as shown here. All that we have done in this case is substituting corresponding quick formulation for convection, which is on the left side, and right side is diffusion, and we already know about it. Again we can rearrange, that is phi at P appears in all that term, and you collect all those coefficients and arrange them together in the standard form, and that is now written here as AP phi P AW equal to AW phi W plus AE phi E plus AEE phi EE. So, this is for the case when the flow is from right to left, and we have already seen separately for the flow from left to right. Now, to get a generic expression, because you have a situation of flow coming from left to right or right to left, we have no idea prior. So, we have to get a generic expression. So, we have to combine both of them together, and that is what we are going to see in the next slide. We have obtained expression separately for each condition. We can get generic expression combining both this condition, and that is shown here. That is AP pi P, that is the node interest, and AW phi W, AE phi E. So, in central approximation or pure upwinding approximation, you had expression only up to here. Now, when you apply quick scheme, you get two additional term, phi at EE and phi at WW. Now, correspondingly, AP is related to neighboring node coefficients as shown here. So, AP is AW plus AE, then you also have AEE and AWW. So, these are depending on the direction of the flow plus FCE minus FCW. You can also put them together in generic form in this way as shown here. So, AW coefficients are written in detail, AWW coefficients written in detail, and AE and AEE. Now, in this expression, if you look at carefully, beta is one new variable introduced, because we have flow coming from left to right as one case and flow coming from right to left as another case. So, when you are actually writing a program, when you are incorporating this quick scheme inside your code, the code should automatically detect the direction of the flow and switch accordingly. Even if it is a quick scheme, switch between nodes according to the direction of the flow. And to enable that, we have introduced a new coefficient, what is written here as beta. So, beta is a coefficient that decides the direction of the flow. Accordingly, the switching between this side, left side or right side will be taken. So, beta is defined. If beta is equal to 1, then FCW is greater than 0, which means flow is from left to right, and beta E is equal to 1, then FCE is greater than 0. Please remember, F stands for flux and C stands for convective flux. So, E stands for east phase. So, FCE means it is directly related to velocity, which is velocity condition on the east phase. So, when you say beta E equal to 1, which means the flow is greater than 0, which is positive, hence it is from left to right. Another situation, if beta W equal to 0 and beta E equal to 0, correspondingly the flux at west phase and the flux at east phase are less than 0, which means the flow is from right to left. So, depending on the beta condition, so in your actual code you find out a direction of the velocity, evaluate FCW. If FCW is greater than 0, you switch to one condition. If FCW is less than 0, you switch to another condition. That is how it is done in code, and correspondingly it is written for coefficients. For example, if you say beta W is equal to 1, if you substitute in this expression for AW, then this particular term vanishes. You can also check similarly for other term. So, when you write a code, the switching according to the direction of the flow is done automatically. Now, though the quick scheme appears good in terms of the direction of the flow and accuracy, combining the merits of central differencing scheme as well as upwind differencing scheme. Now, let us look at specifically merits and demerits of quick scheme. It is upwind biased or upwind weighted scheme. We already seen there are two nodes, one on either side and one extra node in the direction of the flow. That is why it is called upwind biased scheme, because it is in the direction of the flow biased, it is also possessing what is known as a transportive property. And we have done a quadratic fit, so it becomes a third order accurate. Again remember, pure upwinding is first order accurate, central differencing scheme is second order accurate, quadratic scheme is third order accurate. So, by taking one extra node, you are able to improve the order of accuracy to next level. And numerical or false diffusion, which is also called numerical viscosity, is reduced, it is very small, and it has a accuracy greater than central differencing scheme, pure upwinding, even hybrid scheme for the same mesh size. Though these merits are there, it also has its own demerits. Sometimes negative coefficients may happen, and that may lead to what is known as a ill positioned matrix, because we deal with only matrix at the end of the day. If the matrix is not properly formed, then you will not be able to invert a matrix, and that may result in what is known as a stability problem. So, in the case of quick scheme, sometime you may have a situation of ill positioned matrix, and which may lead to what is known as a stability problem. The one more important property is a tridiagonal structure. We are going to see in detail what is tridiagonal matrix and how to invert a tridiagonal matrix. In the case of central differential scheme, we had tridiagonal structure of a matrix, that is, we had one main diagonal, immediately super and immediately subdiagonal. Then there is a separate procedure available to invert that type of a matrix. In this quick scheme, because we have considered one extra node, the tridiagonality of the structure is disturbed and you have to have a separate procedure to invert that matrix. One more demerits, it can give rise to sometime overshoot or undershoot. Let us get an idea of what is overshoot and undershoot with the help of a illustration. What is shown here is one solution finally obtained, and you see here this is a black line which corresponds to solution obtained by analytical procedure or exact solution. If you use pure Upwind with a mesh size 50 by 50, you get solution as shown in blue color, and for the same mesh size if you use quick scheme, then you get solution as marked with the red color. And you can observe between the two, though quick solution reaches the exact solution near for the same mesh size, it also exhibits some overshoots and some undershoots, okay, because it is going below 0, which is kind of unrealistic. So, pure scheme, it is not capturing exact distribution, but there is a diffusion, there is no overshoots or undershoots. This is the property of what is known as a numerical viscosity. So, the numerical viscosity or false diffusion ensures smooth solution, but it does not capture accurately peak or the maximum value, whereas a quick procedure for the same mesh size gets a solution very near to the actual solution. At the same time, it results in what is known as the overshoots and as well as undershoots. Okay. So, in today's class we have seen in detail about quick formulation. I mentioned in detail for two situations, when the flow is from left to right, when the flow is from right to left, how to evaluate the variable value on east phase and west phase accordingly from a generic quadratic interpolation formula. Then we put them together to get a generic expression, and that had one extra coefficient by name beta. Beta automatically ensures according to the direction of the flow the switching terms in coefficients. With this we come to the end of description about all type of approximation. Next class we will see illustration with an example. Thank you.